Now, amortized analysis. Let's record that the target of the split trees is that any m consecutive operations take at most m times log n time. So averagely speaking, each operation would have a log n time, but that log n is called the amortized time bound. For now, we have studied three kinds of time bounds: worst case bound, amortized bound, and average case bound. We say worst case bound is not greater than or equal to, but stronger than. Okay, so the worst case bound is stronger than amortized bound. For example, when we talk about the AVL tree, it means that the worst case bound for each operation is log n. If the worst case bound is log n, then certainly the amortized bound will be log n. So in other words, if it's an AVL tree, it must be a split tree, but not the other way around. If amortized bound is log n, it doesn't mean that the worst case bound can be log n. So it means worst case bound is stronger than amortized bound. And when we talk about average case bound, it's weaker than amortized bound in the sense that in many cases it's almost impossible to properly define an average case. So in order to do average case analysis, usually we would add some assumptions on the probabilities. For example, in the fundamental course, when we analyze the quicksort algorithm, we know that the worst case for the quicksort is n squared, but the average case is n log n. Do you still remember how we proved that? We assumed that for the input data, every permutation is equally likely to happen. With that assumption that we can define average case, and therefore we can obtain the average case bound. But amortized bound has nothing to do with probabilities, so there's no probability assumption, which means no matter what the probability is, amortized bound is the real average of all the cases. But we wouldn't call the amortized bound as the average bound because, to be more accurate, amortized bound is an upper bound of the real average. It's stronger than the so-called average case bound, while we have to assume some probability distributions. To do amortized analysis, we have three methods: aggregate analysis, accounting method, and potential method. Now let's go through them one by one. Aggregate analysis. What is aggregate? What does aggregate mean in Chinese? In Chinese, we translate it as 总和. It's like the total sum of something. So the idea of aggregate analysis is that we try to show that for all n, a sequence of n operations, no matter what they are, takes a worst case time of t of n in total. That's why it's called aggregate. Then we can obtain the amortized cost by dividing the total cost by n. So that's the average for each operation. And we call it amortized cost for each operation. Now let's take a look at one example, a very simple example. In a standard stack, we have two operations like push and pop. Each operation will only take a constant time, just one step, right? And here we have a special stack with push and pop and a special function called multipop. Multipop means instead of popping only one element, it will pop k elements at a time. So this is the pseudocode. Well, the stack is not empty and k is still positive, pop and decrement k. So what is the time complexity of this one? Simple, right? It's either just k if there are k elements in the stack, or if the current size of the stack is smaller than k, it will be the size of s. So it's the minimum of either the size of the stack or this k. Now let's consider a sequence of n operations. The n operations could be push, pop, and multipop on an initially empty stack. This is very important. Initially empty stack. So what is the total worst case time. Here we assume that the size of S is no more than n. So obviously the worst operation is multi-pop. It takes as bad as n steps to pop everything out if k equals n, right? So the worst case complexity for one multi-pop can be as bad as n. For a sequence of n operations, if all the operations are multi-pop n, what's going to happen? Does it mean that we're going to have a total worst case time of n squared? Well, it's okay to say it's big O of n squared because big O means upper bound. So n squared is certainly an upper bound, but it's not a good upper bound. It's just too much. Now think again. What will happen if we really call multi-pop n times? Is it really going to be big O of n for every time that we call multi-pop? Is it possible? Not really. A simple fact is that we can pop each object from the stack at most once for each time we have pushed it onto the stack. So if we want to pop anything, it has to be pushed before, right? So in order to have this multi-pop of n, we have to have n pushes before we call this multi-pop. So the worst case is like we have n minus 1 pushes plus 1 multi-pop with n minus 1. So there are going to be at most 2n minus 2 steps to go. And therefore, the total worst case time is big O of n. So the amortized time for each operation would be a constant. So that's how aggregate analysis works. But it works only for some very simple cases like this. For more complicated problems, it's going to be quite hard to actually calculate the total sum. And that's why we have another method called the counting method. The idea of a counting method is this. Let me read it first. See, when the operation's amortized cost exceeds its actual cost, means the actual cost is better than the amortized cost, we're in good luck. Then we assign the difference to specific objects in the data structure as credit. Credit can help pay for later operations whose amortized cost is less than their actual cost. What does it mean? It's just like what I said before. Like we have a savings account. Okay. When the actual cost is smaller than the amortized cost, it means that we're in good luck. We have some extra time saved comparing to the amortized cost. And therefore, in that case, we would save our good luck as a kind of credit and save it in the savings account. And later on, if the amortized cost is less than the actual cost, means the actual cost is larger than the amortized cost, means it takes more time. That corresponds to the bad luck. Okay, if we're in bad luck, we can withdraw some money from the savings account. We can take some credit to pay for the bad cases. So the trick is to decide the credit, the amount of credit, while we're in good luck. How much money shall we save in the savings account? Okay, no matter how we define those credits, one thing we have to make clear is that we must make sure that the total actual cost must be bounded above by the total amortized cost. So we say that amortized cost is not exactly, if they're equal, it will be exactly the average. But if it's too hard to obtain the exact value of the actual cost, we can at least obtain its upper bound. And divided by n to obtain the upper bound of the average cost, or call it amortized cost, for each operation. Now let's get back to the previous example. We know that the actual cost for push is what? It's 1, right? It takes 1 step to push, 1 step to pop. And this is the actual cost for one multi-pop. Okay, now here comes the magic. Let's define the amortized cost for push to be 2 and 0 for pop, 0 for multi-pop. It looks strange, isn't it? Why? Why do we define the amortized cost in this way? There's ought to be a reason behind, right? Now let's check out the credits first. We start from an empty stack, and credits for push will be what? The credit is the difference, right? It's the amortized cost minus the actual cost. That will be positive 1. For pop, it will be 0 minus 1. We get negative 1. For multi-pop, it will be 0 minus this number, but it's not just this number. You can understand as minus 1 for each plus 1. Do you see the reason here? When we are having the operation push, we are in good luck. So let's save that good luck in a savings account. Let's save $1 in the account. And popping operations are considered as the bad lucks, no matter it's one pop or multi-pop. So for each pop, we have to withdraw money from the savings account. Withdraw $1 for each pop. For multi-pop, it's the same thing. Withdraw $1 for each push. What do we get at the end? Since the size of the stack is never a negative number, therefore the total sum of the credits is never a negative number. It's greater than or equal to 0. And therefore, when we sum up the amortized costs and the actual costs, since amortized cost is the actual cost plus the credit, and the total credit is never a negative number, therefore this is bigger than or equal to the actual cost. And when we sum up all the amortized costs, it's a simple calculation to see that it's either 2 or 0. And when we sum them up, it's big O of n. And therefore, we have just proven that the amortized cost for each operation is a constant. The key difference between this method and the aggregate method is that in aggregate method, we treat all the operations like the same. But in this accounting method, we say the amortized costs of the operations may differ from each other. We assign different credits to different operations. So the hardest part is, how do we know? How can we guess the correct number here? Why do we have to define it to be 2? What if it's 3? What's going to happen if we say replace 2 by 3? Like 311. Will it work? So the hardest part is to guess the correct credits for each operation. And for complicated problems, it's going to be quite hard to do so. So for more complicated problems, we're going to have our third method called potential method. To use potential method, we have to take a closer look at the credit. Okay, in the accounting method, we define the credit to be the difference between the amortized cost and the actual cost. Now, in potential method, let's define this credit to be the difference of two values of the function, and this function is called the potential function. And this D represents the structure of the current problem. So D sub I minus 1 is usually the structure before this operation, and D sub I is the resulting structure after this operation. The potential function is a kind of function to map the current structure of the problem into a number, and that number is called the potential of that structure. So credit is what? Credit actually tells us how much this operation has changed the problem structure. Okay, that's the actual meaning of this credit. Now if we sum up both sides, what do we get? Let's move the actual cost to the right hand side of the equation and sum them up. we can easily see that all those potential values in between will be cancelled out. It's like we start from like d sub 1 minus d sub 0. Next, we're going to get d sub 2 minus d sub 1. So d sub 1 will be plus d sub 1 minus d sub 1. They will be cancelled. So everybody will be cancelled out except the first one and the last one. And we're going to be end up at this equation. So if we can make sure that this part is non-negative, then we can be sure that the amortized total cost is an upper bound for the actual total cost. So the hardest part for using potential method is to define a good potential function. So instead of guessing the proper credit for each operation, we have to guess a good potential function for the current problem structure. Sounds quite abstract, right? In general, a good potential function should always assume its minimum at the start of the sequence. So this number is supposed to be the smallest one, and therefore to guarantee that this part is non-negative. So everything else can work. But how to define a good potential function is another story, and it's quite hard. Now let's again take a look at this simple example first. Okay, with this stack, d sub I is usually defined to be the structure of the current situation. In this case, let's define d to be the stack that results after the i's operation. That's the current stack. In general, the potential function should be able to map the current situation, the current structure, into a number. And that number should be able to somehow represent the current situation. In this case, let's define the potential function to be the number of objects in the stack, in the current stack. All right. Now first, let's check, is it a good potential function? We know that at the very beginning, the stack is empty, and therefore the initial value is 0 for this potential function. And the number of objects in the stack is never negative, so it's always positive. So this function indeed assumes its minimum value at the very beginning, so it looks fine. All right, now let's check the potential difference for each operation. For the function push, this is before. Before pushing, the size of stack is this. And after pushing, there will be one element more than the previous size. So the difference is just 1, which implies that the amortized cost for push is the actual cost, which is 1, plus the difference of the potential function. So it's 1 plus 1 equals 2. Now you can see why we have the number 2, not 3, not any other numbers here. Right? And for pop, this is before, this is after, so the difference is -1. So it implies that the amortized cost is the actual cost, which is 1, then -1, that's 0. That's why. And for multi-pop, before the multi-pop, suppose that the size of the stack is this. Then after multi-pop, suppose we have popped k prime elements out. So the result will be -k prime. Okay, now plug it in to this equation. We see the amortized cost will be the actual cost, where the actual cost is just k prime if we are supposed to pop k prime elements out. And the difference is -k prime, so the sum is 0. That's why we define the amortized cost for multi-pop to be 0. That's where we get 2, 0, and 0. And the rest of the analysis is trivial. We just sum them up, and we get that this one is obviously big O of n, and is an upper bound of the actual cost. And therefore, the amortized cost for each operation will be a constant. And this is, again, a very simple example. Let's try a harder one. Let's try to analyze the splay tree. We claim that the amortized time for each splay tree operation is log n, is big O of log n. And let's try to prove it by the potential method. So step 1, let's try to define the structure, which is simple. We can just define the structure to be the root of the resulting tree. Or we can simply define it to be the resulting tree. It's the same. Okay. The key is this potential function. It's quite complicated to actually get the proper potential function that really works to prove this amortized bond. There are many different ways of defining this function. But anyway, this function, if it works, first of all, it must increase by at most log n over n steps. Otherwise, we won't be able to get this upper bound. And it must be able to cancel out the number of rotations, cancel out those actual costs. So many people have tried many different ways of proving it. And the one that finally works is this one. The function is the sum of all the log of the sizes and S of I, where S of I is the number of descendants of I, with I included. It's just the size of a subtree, with I being the root of that subtree. Okay, so S of I is the size of a subtree, with I being the root. And what is the log of this size? Say, if this subtree is balanced, log of its size is about the same as the height of this tree, right? But it's not accurate, so let's define it to be the rank of the subtree instead of calling its height of the tree. So it's like summing up all the heights of all the subtrees. But then a natural question would be, why do we have to define a rank? Why don't we simply use the heights? Okay, again, this is not a simple question. Let's first move on with this definition and try to prove our conclusion. And then after the class, if you're really interested, I would suggest you to, replace this rank by the height of the tree and plug it into the proof and see what's going to happen. And hopefully you can find the reason behind. Okay? So now let's continue with this potential function. So this is the potential function. It's the sum of all the ranks of all the nodes. With a splay tree, we're going to have 3 kinds of operations: zig, zigzag, and zig-zig. And we're going to analyze each one of them. So first, in the zig case, this is the amortized cost, and this is the actual cost. Actual cost is what? We only need 1 step to do a single rotation to obtain this resulting tree, right? And this part represents the difference between the potential functions before and after. Notice that A, B, and C are not changed before and after. So the total number of nodes are not changed in these 3 subtrees, and therefore their ranks are not changed. So if we do after minus before, they will be cancelled out. Only the ranks of 2 nodes are changed. So this is the after rank of x after rank of p minus before rank of x minus before rank of p. And we claim that it is no more than 1 plus the after rank of x minus the before rank of x. Why? Because this part is negative. It's guaranteed to be negative, right? So before the rotation, p is the root of the tree. So the size of p contains all the nodes in that tree. After the rotation, p is only the root of a subtree. So the size, or say the rank of p, gets smaller afterwards. And therefore, after minus before, this is ought to be a negative number. So it's this part minus something is certainly less than or equal to this part. Okay, so this is the first inequality we obtain for the first case, for the zig case. For the zigzag case, it's more complicated. And again, for those subtrees, their ranks are not changed, and therefore they will be cancelled out. So we only concentrate on the ranks of these three nodes. Okay, and the actual cost is 2 because it's a double rotation. It takes 2 steps to complete the rotation. So this part is the actual cost, and this is before, this is after. And we claim that this part is no more than 2 times the after rank of x minus the before rank of x. And the proof is a little bit tricky. Let's see. First of all, these 2 ranks will be cancelled out. How come? This is the before rank of G, where G is the root of the tree, and therefore the rank is the rank of the whole tree. And after the rotation, X is the new root, and the rank of X is also the rank of the whole tree, and therefore they are the same, so they can be cancelled out. And the next part will be, say, before the rotation, the rank of X plus the rank of P, and take an opposite, is less than or equal to 2 times the negative of the rank of X. Now let's first check out the tree before the rotation. Alright, so according to this figure, obviously you can see that the size of this tree is greater than or equal to the size of its subtree. And therefore, we take log to both sides. We have that the rank since it's before the rotation, so that's rank 1. Okay, so rank 1 of P must be greater than or equal to the rank of X. Then if we add negative signs to both sides, we're supposed to change the direction of this inequality. So we get negative R sub 1 of P is smaller than or equal to the negative of R sub 1 of X. Now see the conclusion, right? We simply add negative R sub 1 of X to both sides. So what we get? We get negative R1 of X. Here another negative R1 of X, so it's negative 2, right? And that's why we get our inequality. So the negative part of R sub 1 of P minus R sub 1 of X is smaller than or equal to negative 2 times R sub 1 of X. Okay, now this part is done. What's left is we have to prove that 2 plus this is less than or equal to 2 times the rank of X after the rotation. And there's a theorem given in your textbook. Now let's check the tree after the rotation. There's a lemma in our textbook saying that for positive integers a, b, and c, if a plus b is less than or equal to c, then we can conclude that log of a plus log of b is smaller than or equal to 2 times log of c minus 2. Now in this tree, obviously we can observe that the size of this tree plus the size of this tree must be smaller than or equal to the size of the whole tree, right? Okay, so what do we get? We get the size of P plus the size of G is smaller than or equal to the size of the whole tree, which is the size of X. Alright, so it's like A is S of P, B is S of G, and C is S of X. If this is the case, then we can conclude that log of A, so what is log of A? That is the rank right? That's the rank of P is after the rotation. So that means rank 2 of P plus log of B, that is rank 2 of G, must be smaller than or equal to 2 times what? Log C, that is log 2, that is rank 2 of X, then minus 2. Now let's move this negative 2 to the left-hand side of the inequality. That's plus 2. Let's add 2 to both sides, so obtain the inequality that we need. So finally, we obtain this inequality saying that in the zigzag case, the amortized cost is bounded above by 2 times the after rank of X minus the before rank of X. And in the zigzag situation, actually everything is similar. You can similarly prove that the amortized cost is bounded above by 3 times the after rank of X minus the before rank of X. So put them all together, we can find the common upper bound for the amortized cost. Right? We just take the maximum is 1 plus 3 times the difference. Now let's sum them up. We get the conclusion of this theorem. Say the amortized time to splay a tree with root t at node x, which means at the very beginning this is node x, and after those rotations it's going to be the root t, is at most 1 plus 3 times the rank of the final root minus the rank of the initial x. And the rank of the final root is just what? It's log n, right? Because t is the root and the size of the root is just n. So the rank of n is log of n. So it's just big O of log n. That completes the proof.